In the last few lectures, we have been talking about work and energy principle, and we said that in general form, work and energy principle is like this. So work and energy. We said that the work of a non-conservative forces, so non-conservative forces, is equal to the change in the energy of the system. So this is equal to delta E, or E2 minus E1, which we said that E is just the sum of the kinetic and the potential energy of the system. And so let me write this down. E is equal to T plus U. So this is kinetic energy and this is potential energy. We also said that in general for the potential energy, we just consider the gravity, the potential energy due to gravity, and also due to springs if we have any springs in the system. So basically this is 1 for spring and 2 for gravity. So this was the work and energy principle in the general format, and we solved a couple of examples for this, but all of those examples, we had this term equal to 0, the work of non-conservative forces. And today we want to solve an example where this quantity is not 0 anymore. So I have prepared an example here where we have a column here, we have a slider on this column. We give this slider an initial velocity. The slider is also attached to a linear spring with a constant k. Initial length of the spring is L. And we are asked to find the velocity of this slider as a function of its position along the column as a function of x. So find the velocity of slider as a function of x, v of x. And we are also given this integral, that this integral dx over the square root of a squared plus x squared is natural logarithm of x plus the square root of a squared plus x squared. So we will see if this comes useful or not. So we are also given as I said, the numerical value of these quantities. K is 100 Newton per meter. L, the initial length of the spring, is half a meter. So this is meter. The velocity, initial velocity, is 6 meters per second. So it's kind of like this slider is attached to this spring on this column, and we hit it, for example, with a hammer and give it an initial velocity of 6 meters per second. And we are also given the coefficient of the friction here. The coefficient of the friction between the slider and the column is 0.4. And you can see that because we have the friction here, friction is a non-conservative force because it just dissipates energy in the system. So we have to use the general form of the work and energy principle. We don't have the conservation of energy anymore here. So just to start solve this, let's see what kind of forces we have on the slider. So we want to just kind of like study the motion of this slider. So if I draw kind of like a schematic of this, let me go here. So let's say this is a column, and we have, this is our particle, this is our slider. So the forces that we have on this, forces that are acting on this particle, the first one is just the gravity. We're going to have the gravity force. Let me use this. So this is going to be gravity. So this is mg, the weight force of the particle. That's the first force. Another force that we have that is acting on this particle is just a spring force. So actually let me just kind of like continue this line. Oops, not with red. Good. Okay, this is not bad. So let's say that the initial position of the particle is here and the spring is at here. when the particle is just when the particle is at x position, so this value here is just x. Now the spring is just kind of like stretch here, and therefore the force of a spring would be kind of like from here to the support of the spring. So let me draw that force here. We are gonna have force of spring this direction. So this would be F of a spring. So this is the second force that we have. Another force that we have is just a friction force. So because the slider is just moving in the downward direction, the friction is always in the opposite direction of motion. So the force of friction would be upward. So here this would be basically friction force. So this is F of friction, F of F. And the last force that we have is just a reaction force between this slider and the column. So because the spring is just pulling this particle, this slider in this direction, we are going to have a normal reaction from the column that is exerted in this direction to kind of like oppose the pulling of the spring. So this would be the normal force that is exerted on the slider from the by the column. So this would be, let's call this N. So these are all the forces that are acting on this particle, and now we can just kind of like start writing down the work and energy principle and see which of these forces are conservative, which one are not, and then calculate the work for those forces that are not conservative. So let me go down here, maybe here. So work of non-conservative here. So I would just put non-CF, so non-conservative forces is equal to E2 minus E1. So from these forces, we said that the work of the energy, the change in the energy due to the gravity, and also if we have a spring, it's just that we consider them as conservative forces. We showed that they are conservative, so they are going to be represented in the energy terms on the right hand side of the equation. For the reaction of the normal reaction of the surface and also the friction force, we don't have them categorized among our conservative forces. So we will consider them on the left hand side of the equation where we calculate the force. So we know that the friction force is definitely non-conservative because it just dissipates energy, but we don't know here about the normal reaction. But because it is not weight, it is not the spring force, we will treat it as a non-conservative force. So here basically we are going to have the work of N, the reaction surface reaction force, plus the work of friction force, F of F, is equal to E2 minus E1. So let's calculate these terms. Let's start with E1. So for E1, we have, this would be the potential energy plus kinetic energy. So this would be T1 plus U1. We know that T1 is equal to 1 over 2 m initial velocity squared. So we said that we are giving it V0 initial velocity, which V0 is equal to 6. By the way, the mass of this, we need also the mass of this slider. So let me write down m, for example, 2 kilogram. So the kinetic energy would be 1 over 2 m V0 squared here, which would be 1 over 2 times V0, which is 6 squared. So this would be 36. For U, we have to calculate the change in the potential energy due to gravity, and also the energy is stored in the spring. So at initial position here, the spring is at rest, so there is no energy stored in the spring. So here we said that this U1 is just U spring plus U gravity. The energy is stored in the spring, as I said, is just 0, because at the beginning the spring is not stretched, so there is no energy stored in the spring. And for the gravity we have to consider a reference position. So if I could just consider the initial position as a reference position, so let me draw a line here. So this is a reference for gravity. Reference for gravity. So gravity is in this direction here. We have here. Let me write this better. G, which is equal to 10 meter per second squared. So this is the reference for gravity when the particle is just going in the direction of the gravity, going downward here, and this distance is equal to x. Its potential energy due to gravity actually decreases here because we are going in the direction of g. If we go in the upward direction, the potential energy due to gravity increases. But because here we are going downward, and by down we mean in the direction of the gravity, the acceleration of gravity, the potential energy due to gravity decreases here. So here we are going to have, if this is the reference point, we are going down by x. So the initial potential energy would be 0, and the second, the kind of like final potential energy due to gravity would be minus mgx. So here, because this is the reference and we are at the reference of gravity at the beginning, the potential energy due to gravity would be 0. So here we have 0 plus 0, which would be 0. But for U2, we are going to have, again, U of spring plus U of gravity. Because we explained this, let's just write this down, and then we calculate the potential energy of the spring. So spring plus, here would be minus mgx. When we are going downward by x, the potential energy due to gravity decreases, and that's why we have the minus sign. So let's also calculate the energy stored in the spring when we have gone down by value of x. So we have to calculate the length of the spring at this position, and then subtract the initial length of the spring, so that we can have the elongation in the spring. And we know that the energy stored in the spring would be 1/2 times the coefficient of spring k times the elongation squared. So U of a spring here, U spring here 2 would be 1/2 k, and let's show the elongation by delta. This would be delta squared. So what is delta? So delta would be L2 minus L1. What is the length of the spring here at this position? So we have this value. This is L, which is 0.5 meter, and we have this also, this value here. We have a triangle with 90-degree angle here. So here, because we have this value, we can obtain the length of the spring based on x, and also the initial length of the spring. So if we call this L2 here, L2 would be L squared, square root of L squared plus x squared. So this would be L squared plus x squared minus the initial length of the spring is just L. So this would be the elongation in the spring. And we can just put in the numbers. So L was 1 over 2, it was half a meter, so that's 1 over 2 squared would be 1 over 4 plus x squared minus 1 over 2. Therefore, we can just substitute this value here and just calculate the energy stored in the spring. So it would be 1 over 2 k. We have the value of k, I think is 100. Yes, it is 100 times 100 times delta squared, which would be 1 over 4 plus x squared minus 1 over 2 and the whole thing is squared. So this would be 50 times this parenthesis squared. So let me write down here 50. So 50 times this parenthesis. So we have T1, U1, U2. Let's also calculate T2. So the kinetic energy when we are at x, at the second position here. And because we don't know the velocity here, that the question is actually asking about the velocity, we want to find the velocity as a function of x. So we just consider an unknown value for velocity here, v of x. The velocity of the slider along the column would be a function of x. So at this position at x, we said that the velocity is just v of x. So because we have again the mass and also the velocity as an unknown function, we can write down the kinetic energy as 1 over 2 m v of x squared. So m was 2. Let me check here. M is 2. And we have here, this would be 1 over 2 times v of x squared. So this would be v of x squared. So now we have all the terms that we need to calculate the energies E2 and E1. So basically we can write down here W of n plus W of friction is equal to E2, which is v of x squared plus this value, the energy is stored in the spring, and also energy due to gravity here. Remember that the potential energy had two terms. We calculated the gravity term, and this is the spring term. So this would be minus mgx plus 50 square root of 1 over 4 plus x squared minus 1 over 2. So this is basically E2. So E2 minus E1, and E1 here, it was just 0 because the way that we considered the reference for gravity, and also because, or actually no, the potential energy was 0. The kinetic energy at the beginning was not 0. So U1, T1 was 36. So minus 36. So the work of non-conservative forces is equal to the change in energy, and we can see that the change in the energy is a function of x here. So now we have to calculate these forces, the work due to non-conservative forces, because our goal is just to find the velocity as a function of x. So we have to also calculate these works terms. So for W of n, we have, so basically here we have to use integrals because the force of the spring is changing when the particle is moving here. As the particle is just going further down, the elongation increases, therefore the spring force increases. So the spring is just pulling this particle harder and harder, and therefore this reaction is just becomes larger and larger because this is kind of like opposing the spring force. So the N would be kind of like a function of X along the column. So N would be function of X, and we can actually calculate it here. So we can say that because this particle is just moving in the vertical direction and there is no motion in the horizontal direction, so we can just use Newton's second law, and because the acceleration is 0 along the horizontal direction, we can find N, the reaction force, as a function of the spring force, and we know that the spring force is a function of X. So basically here this would be, so let's write down the integral. This would be from 0 to X N dot dr, and dr is just displacement. So what is N? N is, so I have to just again draw this free body diagram here, kind of like this is N and this is spring force, so F of a spring. Let's call this angle theta. So if this is theta, we can say that, so for N we can say that sigma F of horizontal, I don't use X here because we are using X for the vertical coordinate, so F in the horizontal direction should be M A in the horizontal direction. Because this is equal to 0, the particle is not moving in the horizontal direction, so we conclude that the sigma F in the horizontal direction should be equal to 0. And this means N minus N, N is just going, is going to the left, plus F of a spring times sine theta is equal to 0. And we can actually calculate sine theta here. So because this is the angle theta, we have this value here, this is L, and this side of this triangle is also X. This was L2, the second length of the spring. So sine of theta would be L over L2. So here we get N is equal to F of S sine theta, which would be, F of S would be K delta times sine theta, which is L over L2. So this is equal to, let me actually just go here, right here, so that we can use this as space. So N would be K times delta, delta is just L2 minus L1 times L over L2. And this would be KL L2 minus L1 over L2. So this would be KL 1 minus L1 over L2 equal to KL. K was 100, L was half a meter, so this would be 50. And here we have 1 minus L1 was half a meter again, and L2 was just square root of half a meter squared, which is 1 over 4 plus x squared. So this is basically the value for the normal reaction between the particle, between the slider and the column. So N is equal to N of x, which is 50 times 1 minus half over 1 over 4 plus x squared. And now that we calculated normal reaction here, we can also write down the friction force, because by definition the friction force is just mu, the coefficient of friction, times the normal reaction. So F of F, we will see that the work of this force is actually 0, because N is just here in the horizontal direction, and dr displacement is in vertical direction. So these two quantities, these two vectors, are normal to each other. So the work of the normal force would be 0, but the reason that we calculated the normal force was that we want to calculate the friction force, because as we will see, the work due to friction force is not equal to 0, and we have to calculate it. So here we conclude that F of F, friction force, is equal to just mu n of x, and we have n as a function of x. So now I can just calculate those integrals. So W of n is equal to integral of n dot dr as we go from 0 to x. So this would be n, the value is just going to be 0 to x, n of x, let's call the horizontal direction I, and the vertical direction j. So this would be n of x, actually minus n of x in the I direction, dot product by dr. dr would be dx in the j direction, because we are going in the vertical direction. So this is because I dot j is equal to 0, this is equal to 0. So the work due to normal force is 0 here. And for the friction, we can say that W of F of F is equal to integral from 0 to x F of F dot dr. So this would be, we can actually here use kind of like the definition of dot product, which would be the value of this force times the value of the displacement times the sine of angle between them. Or here just say that F of F can be kind of like decomposed to two vectors, one normal to the column and one along the column, and the force due to the normal component is again equal to 0. Same thing, similar to the work that we had for n, and the work due to the component along the column is not 0, and we have to calculate it. So this is basically, if that angle is theta, we showed it here. I think it was here. So that if that angle is theta, this is basically F of F would be mu n, and it is in the upward direction, so minus mu n times dr, which would be dx, times the sine of angle between them, so that's sine theta. So again, if I have the column here, and if this is the particle, if this is the force, the spring force, actually the friction force. So the friction force actually has just one component. Sorry, I kind of like made a mistake that I explained the friction force as a spring force. No, the friction force is just upward along the column axis. So it would be, the displacement would be downward, the friction would be upward. We can actually write down the vector product here. So let me erase this. So it's better to write it this way. Sorry about that. So here we have 0 to x integral F of F, which would be mu n of x in the j direction upward. Dot dr is just dx in the minus j direction. So this is dx minus dx j direction. So j dot j is just 1 and we have a minus here, and that's why we had the minus sign over there. So 0 to x minus mu n of x dx. So, and it's better to kind of like change the argument of integral here. It's just, that's kind of like mathematically correct. So I will write down w f of f is equal to minus mu integral 0 to x n of, let's call it u du. So I just changed the name of the argument so that we can have everything correct. So n of u, this is. And this would be minus mu integral 0 to x, and we had n, so this is the value of n, 50. So this is 50 times 1 minus half over 1 over 4 plus u squared instead of x. So, and this is du. So this would be 50 times mu here is just 0.4, so that would be 20. So this is going to be minus 20 here, integral 0 to x, 1 times du, so that's du, and here plus, or minus actually, minus integral 0 to x. We can actually bring the half also outside of the integral. So this is minus 1 over 2 integral 0 to x du 1 over 4 plus u squared. So the first integral is just easy. This would be x. So this is minus 20. This would be x. So x and x, this would be u at x minus 0. So that would be x minus 1 over 2 this integral 0 to x du square root of 1 over 4 plus u squared. And if you notice, you know, we had a formula for the this integral at the questions. So here this integral dx over a squared plus x squared is just the natural logarithm of this quantity. So we can use this formula to calculate the integral over there. So this would be minus 20 times x minus 1 over 2 natural logarithm of, so that was x, which is here, plus square root of x squared plus a squared. So here our a squared is just 1 over 4 and a is just 1 over 2. So this would be x squared plus 1 over 4. Actually, I should put u and then I have to, so let me clear this. So this would be u plus a squared plus u squared. And we have to calculate this at 0 and x. And this would be minus 20 times x minus 1 over 2. So that would be natural logarithm of x plus 1 over 4. So this is 1 over 4. Over 4 plus x squared minus, so this would be here, minus 1 over 2 is just outside of this integral. So the value of this quantity at u equal to 0, which would be natural logarithm of a square root of 1 over 4, which is 1 over 2. So minus natural logarithm of 1 over 2. So that's the total forces due to that's the total work due to non-conservative forces, and this quantity is equal to change in the energy. So we will have minus 20 times x minus 1 over 2 here, natural logarithm of x plus square root of 1 over 4 plus x squared minus ln 1 over 2. This is equal to the change in the energy that we had here. So let me find that over here. So this was the work we calculated this, and this is equal to this quantity. So let me see if I can copy this. So you can see that in this equation that we got at the end, there is only one unknown, which is the velocity of the particle. So here, that was the work of non-conservative forces, and this was a change in the potential energy. And in this equation, we can easily just find the velocity as a function of x, the position of a slider along the column. And actually, one good kind of like practice here would be to see how far the slider would go downward here. So in order to find the maximum displacement that the slider gets due to this initial value, we can just put v of x equal to 0 in this equation, and we find an algebraic equation on x. And if we solve that equation, we get the maximum displacement of the slider. But this was basically our goal, to find the velocity. You can just simplify this to kind of like bring everything to the one side of the equation and have v squared in another side of the equation, and just take the square root of that, and that would be the velocity of the particle. The next topic that we want to start here is angular momentum and impulse. So angular momentum and impulse. Let me change the font size of my pen here a little bit. Okay, so you are all familiar with the concept of a linear momentum and impulse. We will do a quick review here. So then from there we start to present the definition for the angular momentum and impulse and solve a couple of examples. So for the linear momentum, so this is just basically quick review on linear momentum and impulse. So we said that the linear momentum of a particle that is moving with the velocity of v, so let's say we have a particle with mass m, and it is just moving with the velocity of v. We said that the definition of linear momentum for this particle is just m times v. And momentum is in general, linear momentum in general is a vector quantity. And then we said that if we use the kind of like the second law of Newton, we can get an equation for the impulse. So we can write down for this particle at any moment, we can write down the Newton formula, which is ma is equal to f. Basically, let me write it the other way. This is true in any time t. So it's better to show f of t at any moment t. This is equal to m a of t. And for here we said that this acceleration is basically the derivative of velocity. So this is m derivative of velocity vector over time. And here if we kind of like rewrite this equation, we get f of t dt multiplying both sides by dt. We get f of t dt is equal to m dv. And now if we integrate both sides of this equation, so if we integrate both sides, here we get the integral of f of t dt is equal to m dv, and this would be m v from, let's say, initial, so let's say particle is just going from here, from A to point B. So particle is just going on a path from A to B. So this would be mv a b, and this would be m v of b minus v of a. Or we can denote the initial and the end position by 1 and 2. Say that this is 1, this is 2. So we will have f of t dt is equal to m v2 minus v1. Or basically mv, we said that is just equal to linear momentum. So we can say that mv2 is just p2 and mv1 is just p1. So this would be p2 minus p1, or delta p, the change in the linear momentum. So this quantity here on the left hand side of equation, we said that this is the impulse that is exerted on particle m. So basically here f of t dt is equal to, and let's say we start from initial time t equal to 0, and the time that it takes for the particle to go from A to B or from position 1 to position 2 is just delta t. So this integral would be from 0 to delta t. F of t dt is equal to delta p. The difference, the change in the momentum when the particle is at the position 2 minus the difference in the momentum of the particle between point 2 and point 1. And we call this quantity impulse. And this was change in momentum. So change in p. And basically we said that the impulse is equal to change in the momentum. And if we don't have any impulse, if this quantity is equal to 0, the change in momentum is equal to 0, and therefore we have the conservation of linear momentum. And we had a couple of cases that this impulse was equal to 0. So for example, for deterministic forces, for the forces that we have a formula for them, the value of this impulse, if delta t is just approaching to 0 in a very short amount of time, this term would be 0, and therefore we have the change of momentum equal to 0. We have the conservation of momentum. So basically, kind of like a rough definition, we said that for the forces we have either deterministic forces, or non-deterministic. For the deterministic forces, just this is a rough definition. We said that the forces that we have a formula for them, a value for them. So example of this would be, force of gravity, friction. These kind of forces that 100 Newton, if a value of force is just a constant force. And for the non-deterministic force, we said that these are the forces that we don't have a formula, we don't have a number for them. Again, these are kind of like a rough definition. An example of non-deterministic force would be, let's say we throw a ball with the velocity of v to hit a wall here. When the ball hits a wall, there is going to be a force between the ball and wall, and we said that force is a kind of like a non-deterministic force. It's a kind of like impact, and that's where the definition of impulse is coming from. So we are saying that for the deterministic forces, for known forces, the impulse, if delta t is going to 0, is equal to 0. So there is no impact associated with the deterministic forces. But for non-deterministic forces, their impulse is not equal to 0. So here we are having an impact, and therefore the impulse would be non-zero. Or another example of this would be, let's say we have two masses on kind of like two cars on a wheel here, and let's say there is a rope that connects these two masses or two cars to each other. So this is A and this is B, and at the beginning the kind of like the rope is loose, but then the mass B starts to just move, for example, to the right with a velocity, so here v, and so this mass starts, as it starts going to the right, the rope becomes kind of like a stretch, and at some point the rope kind of like exerts an impact on the mass A, and therefore causes A to also to move. So that force, that kind of like interaction force between this rope or between this mass and this mass, at the exact time the rope is just straightened, that's the kind of like impact like forces. It's a non-deterministic forces. So yeah, that was a definition, kind of like a rough definition for deterministic and non-deterministic forces. And we said that the impact or impulse of deterministic forces if delta t is going to 0. So in a very, very short amount of time, this is equal to 0. But impulse of non-deterministic, so non-deterministic forces, when delta t is going to 0, this is not equal to 0. So this was for linear momentum and impulse. And a famous example of this was kind of like when we had two balls hitting each other, that when we had an impact between two balls. So for example, when we had here, for example, ball A with 2 kilogram mass, it is just going, for example, with 10 meter per second, and we have another ball here which is 5 kilogram, for example, and it's going with 5 meter per second. And the question, these kind of problems were that what happens after the balls hit each other, what happens after the impact. And we using kind of like the concept of coefficient of restitution, we will and using also the linear conservation of linear momentum for the whole system, we were able to calculate the velocity of these balls after the impact happens. So we had the kind of like coefficient of the restitution. This is a quick review, as I said, coefficient of restitution, and basically we had three kind of impacts. If E was equal to 1, that means that we had elastic impact. And the meaning of that was that there was no kind of like energy dissipation in the system. When these two balls hit each other after the collision, if we calculate the energy, the kinetic energy of the balls, it is the kinetic energy basically doesn't change before the impact and after impact. If E was equal to 0, we had plastic impact, and if E was between 0 and 1, we had elastoplastic impact. So this was kind of like the famous example for conservation of linear momentum. And now today, as I said, we wanna study the angular momentum and impulse. And this was just a quick review. So just in a similar way, let's go ahead and define the angular momentum and impulse, and we will see how we can use this concept to solve problems. So for angular momentum. So again, let's assume that there is a particle. So let's say that we have a coordinate system here, x, y, and z. So basically this is x, for example, this is y, this is z, and this particle with mass m is just moving on a path here. So the definition of angular momentum for this point, for this mass as it is moving with the velocity of v along this path. Let me use another color here. So velocity should always be tangent to the path here. Let's say this is the velocity, so v. And we have another point here, for example, point O here, that we need to use this point in the definition of angular momentum. This could be any arbitrary point. So the definition of angular momentum would be here L. We show the angular momentum with L, and it is a vector quantity. It is equal to R, so L about point O here, or about point O is equal to R cross P, the linear momentum of particle M. So what is R? R would be the vector that connects from A to the particle. So this would be R. That's why we have to have a reference point for calculation of angular momentum. And as I said, we can use other points. We get different value for the angular momentum. But as we will see the change in the angular momentum is important, and it is a physical quantity. So that's why it doesn't matter which point we consider for calculating the angular momentum. There are points that makes our life easier in solving problems, but this is basically the definition for angular momentum. So it would be L times P, and here P is just a linear momentum, so P is just m v. So I can write down this is equal to R times m v. That's the definition of angular momentum. Now let's just sometimes they also show this angular momentum by h also, so just different symbols here. So h about point O. Let's now take derivative of both sides of this equation with respect to time. So basically we will have d h of O dt is equal to d over dt r cross mv. Similar to the process that we had, to the procedure that we had for the linear momentum. Remember that the linear momentum we had the Newton law F equal ma, and then we wrote down m a as a derivative of velocity, and we obtain an integral that f that dt integral of f dt is equal to change in linear momentum. And here we want to kind of like obtain the same thing here, but for angular momentum. So if I calculate this derivative here on the right hand side, we will have dho, so this is a change in the angular momentum, over dt is equal to, this would be the derivative of the first quantity cross the second term, plus the derivative, the first vector cross the derivative of the second vector. So this would be dr over dt cross mv plus r cross d over dt v. So dr over dt is just basically v, and v cross v is equal to 0. So we can write down here v cross v plus, and assuming that m is constant, we can just write down m r cross a. Or actually it's better to just keep the m over there with v, because ma, we know that ma is equal to force, so I can write down here r cross, again assuming that m is constant, this would be m dv over dt. So we have dho over dt is equal to, v cross v is 0 basically, the cross product of a vector by itself is 0, and we have here r cross dv over dt is just a acceleration, so this would be ma, and this is basically r cross f. And we know what is r cross f. This is a definition of moment here. So we have m, the moment associated with force f around or about point O. So we have dho over dt is equal to mo. Now we can multiply both sides of this equation by dt, and we get dho is equal to mo dt. And here is the point that we do the integration. So we say that the integral of dho, and let's say that, again, the starting point, the time is 0, and at the end point it takes delta t for the particle to go to the end position. We have the integral of dh from 0 to delta t is equal to integral of mo dt 0 to delta t. And here, so I can write down, this would be h2 minus h1, so this would be ho2 minus ho1 is equal to mo dt. So this starts to look like the equation that we had for the linear momentum. So I can just kind of like rewrite this as this: 0 delta t mo dt is equal to delta h, the change in the angular momentum. And we call this term, the integral of mo dt, we call this angular impulse. So remember that the linear impulse was just f dt, and for the angular impulse we have the integral of mo dt. So this is angular impulse. So the angular impulse is equal to the change in the angular momentum of the system. And Again, there are cases that this quantity would be equal to 0, that we don't have any angular impulse, and therefore we are going to have the conservation of angular momentum. So if this term is equal to 0, if integral 0 to delta t mo dt is equal to 0, then we have conservation of angular momentum. And so now the question is that when is this term equal to 0? So this term could be equal to 0, for example, when f is equal to 0, or when f is just passing through point O. So f is just, if O is in the kind of like direction of the force F, or is just O is on the same line that the vector F, the force F is acting, then the moment of force F would be equal to 0. So if F equal to 0, or O is on the acting line of F, or another case that, so this is point O. Another case that this term, this angular impulse term, could be 0 is that when we have a deterministic force and delta t is going to 0. So if the deterministic force and delta t is just approaching 0, then this term would be equal to 0, and basically we have HO1 is equal to HO2, conservation of angular momentum. So now, just using this concept, we'll start to solve a few examples here. The first example that we want to solve here is a particle A that is attached to this link OA, and it is rotating on this disk around this axis. And we are asked to find the angular velocity of this link OA at t equal to 5 seconds. So the force 100 plus 3t is acting on this link OA, and it always has an angle of theta with this OA, which theta is equal to 60 degrees, and we have all the other parameters required to solve this problem. So the mass of this particle is 15 kilogram. The particle starts its motion from rest, so the initial velocity is equal to 0, and there is a coefficient of friction that is associated with the movement of this particle on this disk. So as the particle is just rotating on this disk, there is a friction between the particle and the disk. So this coefficient is equal, let me get the yellow color here. So this is 0.3. So this is kind of like an example that we can solve by concept of angular momentum and impulse. So here I can use our equation, which was the integral of 0 to delta t mo dt, and here the point that we will use to calculate the moment is just point O here, the center of this disk. As the particle is just rotating around this axis, the best point to consider for calculating the moment is just point O that is placed on this axis of rotation. So mo dt is equal to delta h, the change in angular momentum, and this would be HO2 minus HO1. So let's calculate these quantities. For HO1, because the particle starts its motion from rest, so this would be basically R cross MV1, R1 cross MV1, and here because V1 is equal to 0, this is equal to 0. HO2, the angular momentum after 5 seconds. So here the initial position just refers to the starting moment of the motion, and the second position here just refers to the angular momentum after after 5 seconds. So here we have HO2 is equal to R2 cross mv2. So this is equal to, so we know that the velocity of this particle, so based on all the cinematic that we have had, during the first half of the semester, we know that if we write the velocity of A based on O, it is always going to be normal to this link to the R direction. So here R would be from O to A, no matter where particle A is on the disk. So if this is R, the velocity is going to be normal to this link in the disk plane, because basically we can write down VA is equal to VO plus omega cross R, and omega cross R would be a vector that is normal to this vector, normal to this link, and it is in the disk plane. So I can write down this R2 then, because these two, the R and the velocity are normal to each other, this cross product basically would be the magnitude of the first vector times the magnitude of the second vector times sine 90 degree. And because sine 90 degree is 1, basically we get the magnitude of the first vector times the magnitude of second vector. So and it is also good to note that the h here would be in this. So if this is x and let's say this is y in the disk plane, this would be in the z direction. H would be in the z direction. M would be in the z direction. Why? Because so for the m we will have r position vector times force, which is in the disk plane. So the result of that cross product would be a vector that is normal to this plane. So it would be along the z-axis. Same thing for the h. So mv, we know that v and r, both of them are in this plane, the disk plane. So the cross product between them would be normal to that plane, so in the z direction. So therefore we can kind of like drop the vector notation here, because this is basically all of these quantities, all of these vectors are in the z direction, and we can just write down a scalar version of this equation. So this would be, just to write it down here, this would be R2 mv2 sine pi over 2, and this would be in the k direction, in the normal to the disk plane direction. So therefore, let's just, this would be also 0 in the k direction. So this is 0 is just 0 I j k. So this would be 0 I plus 0 j plus 0 k. We can just consider the k component, because this equation is true for all the components, and we know that these quantities have only one component in the k direction. We can turn this into a scalar equation and write down 0 delta t mo dt is equal to HO2 minus HO1. Basically, this is how we can think about writing this equation in the scalar format. Everything in the k direction, and we are just dropping the k. So for H2, we can calculate this quantity. We can say that H1 was equal to 0, so HO1 is equal to 0, and HO2 is R, the magnitude of R, which is the length of link OA, and the length of link OA is 2 meters. So I can say that this is equal to OA times MV, and we can say that M and we said that V is going to be equal to R omega, the magnitude of velocity. So this would be again R, and R is just OA omega. So this would be M omega magnitude of OA, the length of OA squared. So for H2 we can write down HO2 is equal to M is 15, I think here, yes, 15 times omega, which is an unknown, we don't know, and OA is just 2, so this would be 2 squared. So this is 4 times 15, that would be 60 omega. Okay, so that's for the angular momentums. And now let's calculate this angular impulse term. So this is basically 0 delta t mo dt. So this is the moment of all the forces about point O. So what are the forces that are acting on this particle? Well, first we have this force F, which is a function of time, 100 plus 3t. The second force that we have is just a normal reaction between the surface of the disk and the particle. The third force that we have is just a gravity, and the fourth force that we have is the force of friction. But the point here is that because this particle is just moving in the disk plane, so the force of gravity and also the surface reaction, they are in the z direction, and they are always going to be normal to this OA. So basically, if I want to calculate their moment will actually cancel out with each other, because the particle is not moving in the vertical direction. So the normal force would be equal to the weight, and therefore, but in the opposite direction, and therefore the moment of those two forces about point O, they will cancel out with each other. So we can say that. So here for this, we can say no motion in z direction. So basically, sigma f of z should be equal to 0, and therefore we have mg minus n is equal to 0, and therefore n is equal to mg. So if we calculate the moment due to these forces, because they are in the opposite direction, so basically, let's say this is point O, this is A. Let me use another color here. This is A. So the force of gravity would be in this direction, and the force of surface, the normal reaction of the surface, would be in this direction. Let me use another color. So for example, here. So this is normal force, and this is the weight force, mg. And if we calculate the moment of these terms are not 0, but they cancel out with each other. So that's why we don't consider them in this equation. We can write them down, but at the end they will cancel out. So that's for the moment of these two forces. We have two other forces here, the force F and also the friction, that we have to calculate their moment about point O. So here, this would be 0 to delta t mo dt would be equal to 0. Delta t is just equal to 5. We want to see what happens after 5 seconds. What is the angular velocity after 5 seconds? So this would be the moment of force F, which we have it as a function of time. But here the force of this force has an angle with the r, which is constant at every instant. So again, the cross product of these two vectors r cross f would be the magnitude of this times the magnitude of OA times the sine of the angle between them. So this would be OA, which is 2 meters, times f, which is 100, plus I think 3t. Yes, so 3t times t times sine 60 degree. So let me actually erase this equation from here. Okay, so over here n was equal to mg. So this was the moment due to force F about point O, and also we have to calculate the moment due to friction force. So the point here is that the friction force is also going to be normal to this OA. And the reason for that is that because this particle, the velocity of this particle is normal to OA in the plane of the disk, the force of friction will kind of like oppose the motion of the particle, so it would have the same line of action as the velocity, but in the opposite direction of the velocity. And because the velocity is normal to this OA, so here if the particle is just rotating this way, the velocity would be this direction. Let me draw it here. So let's say this is the velocity v, and this angle is just 90 degree in the plane of disk. So the force of friction would be up in the opposite direction of v, and because v is just normal to OA, the force of friction will also be normal to OA, and therefore its moment about point O would be just OA times the friction force, but in the minus direction. So this would be equal to minus f of f times OA, which is 2 dt. So what is the force of friction? So f of f is equal to just mu n, and mu is equal to the friction coefficient 0.3, so therefore we will have 0.3 times n, and n is equal to mg, so this would be n is equal to mg. 0.3 times mg, m was 15, g is 10, so that would be 150 times 0.3, which would be 45 Newton. So therefore the integral would be 0 to delta t, which is 5, 2 times this quantity. So sine 60 is a square root of 3 over 2, times 2 would be a square root of 3. So this would be 100 square root of 3 plus this would be 3 square root of 3 times t minus f of f times 2. F of f was 45, so this would be 90 dt. And this is easy to calculate, this integral, so this would be 100 square root of 3 minus 90, 100 square root of 3 minus 90 times 5 minus 0, the limit of the limits of the integrals, integral minus 3 square root of 3, it would be t squared over 2, and we will have 5 squared minus 0 squared over 2, and that's it. We had this 90 term. So this would be 100 square root of 3. So let's say that the square root of 3 is about 1.7. So a square root of 3 approximately 1.7. So this would be 170 minus 90 times 5. So this was separate here. 170 minus 90 times 5 minus, here again 3 square root of 3 times 1.7 times 25 over 2. So this is a number we can calculate this. Let's actually use the calculator here. So this would be, and now that we have the calculator, we can actually use the exact value of a square root of 3. So this would be 100 times square root of 3, 173. This should be times 5. It's equal to 866. Let's just round the numbers. Minus, that would be a square root of 3 times 3 times 25 is equal to this over 2. So this is, let's say 65. So this is approximately. So 166 minus 65, this would be 100.01. So now this quantity was the impulse on the particle, and we know that the impulse is equal to change in the momentum. So this would be 801 is equal to h2 minus h1, and we had the expression for h2. So for h2, it was 60 omega and h1 was 0. So this is equal to 60 omega minus 0, which is 60 omega. So omega is 100.01 over 60, which is, so 100.01 divided by 60, which is 13.35 radian per second. So that's what we were looking for, the angular velocity of this particle. And these are kind of like examples that still we are able to solve them with kind of like with using Euler equation, which we haven't introduced yet. So here we are using the concept of angular momentum, or in the previous examples that we were using kind of like the concept of energy, or these problems that we have the concept of angular momentum. There will be problem that it would be really easy to just use the concept of energy or angular momentum to solve them. And there are some of the examples that it's very hard to use. It's very easy to use kind of like the straightforward Newton approach instead of energy approach, or using Euler equation, which we will introduce. Instead of using the Euler equation would be easier for some problem instead of using the angular momentum concept. And there are problems that are kind of like borderline problems that you can solve them with both approach. So in a linear case, you can solve them with Newton approach or energy approach, and for kind of like this angular problems that we have the rotation, we can see that again we can use kind of like the concept of either Euler equation, angular momentum approach, or energy approach again for rotation. So this is one of the example of those problems that we can also solve with the Euler equation. But it's good to see how we can use the concept of angular momentum and angular impulse to tackle this problem. So for today we are going to solve another example. I will write down the question and we will go through it. This is absolutely one of my favorite examples for the concept of angular momentum. And we all kind of know about this. So if you have ever played with a swing in the park, or if you have seen other people playing with a swing, you have noticed that. So we kind of all know about this, that if we start from an initial angle, let's say theta 1, and if we straighten and bend our knees in a particular way, that again we all know about this, but we will explain this in this problem. If we straighten and bend our knees at a certain rate, we can reach kind of like a height that is greater than our initial place that we started the motion. So it's kind of like seems that we are violating the conservation of energy, because one can argue that okay, at this initial height you have a certain potential energy due to gravity, and your velocity is 0 at the beginning, but at the end again your velocity is 0, but you are reaching kind of like a higher point, and that kind of like causes more potential energy due to gravity. So how is that possible that you have a certain potential energy at the beginning, but you end up with a higher value in potential energy at the end? So we want to see what happens here when we do a straighten and bend our knees when playing with the swing. So the way that we all do this is kind of like, so when we start our motion, let's say with a velocity of 0, exactly, or just approximately at the time that we are at the center position here, we kind of like, if we straighten our knees and then go high, and then on the way back in the middle, if we bend our knees, if we do this over and over, we will see that we are kind of like pushing ourselves to higher height here. So we want to see what happens here. Basically what happens here, so I have kind of like shown this person that is playing with the swing at 4 moments. So the initial moment when the velocity is 0 and the person is at a certain height from a reference, let's say from ground. Then exactly at the center, the person just straighten his or her knees at the middle when they are in the middle. So at this point, what happens basically is that the distance between the center of mass of this person to the pinpoint of the swing changes. So let's say here, because the knee is just bended here, the center of mass would be closer to the ground. But when the knee is just going upward in the straighten, the center of mass for this person just shifts a little bit to the higher point from the reference ground. And we will see that this is basically this kind of like changing the center of mass causes the swing to kind of like to go to a higher values, higher thetas than the person initially started with. So here we have assumed that when the person is just has his knees bended, the distance between the pinpoint and the center of mass for that person is 3 meters, and by just straightening their knees, that point just shifts 0.3 meter toward the pinpoint. So now the distance between the pinpoint and the center of center of mass for this person is 2.7 meter, and we will see how that causes the swinging, the more swinging of the swing. So here, just to kind of like analyze what happened, let's just go from T1 to T2. So again, T2 and T3 are exactly in the middle, are just very, very close to the middle position, but just to distinct between them, I have just shown them this way. But basically, they are very, very close. They are just that moment that the person starts to just move his knees and just change its center of mass, the position of his center of mass. So from going when we are going from this position to this position, we can write down the conservation of energy for this person. So basically, the person here is just changing its potential energy to kinetic energy. So we can write down the change. So basically, conservation of energy, T1 to T2. So we can say that, let's say that this is the reference point. Let me show this. So here is just a reference point. Here, the distance of this person, it would be equal to 3 times like 1 minus cosine theta. So we can say that the U1 is equal to, it would be mg, this value above the ground. So it would be 3 minus cosine theta, minus 3 cosine theta. So it would be mg 3 minus 3 cosine theta. What is U2? Because we are at the reference, there is no potential energy in the system. So U2 is equal to 0. On the other hand, K1 is equal to 0 kinetic energy, or T1. T1 is equal to 0. Kinetic energy at the beginning is equal to 0 because the person doesn't have any velocity. But T2 is not equal to 0 because now the person has a velocity. So T2 would be 1 over 2 mv squared, which v is unknown. But now we can use the conservation of energy to calculate v. So I can say that U1 plus T1 is equal to U2 plus T2. So U1 plus T1 is equal to U2 plus T2. So here U1 is equal to 3 mg1 minus cosine theta plus T1, which is 0, is equal to U2 equal to 0 plus T2, which is 1 over 2 mv squared. So we can cancel the m's here, and we get 3g 1 minus cosine theta is equal to, or just multiply both sides by 2. Here we get v squared, and therefore v would be square root of 6g, and g, let's say g is 10, that would be 60, 1 minus cosine theta. This would be 60 times 1 minus square root of 3 over 2. So basically, again, 60 minus 30 square root of 3. And let's say a square root of 3 is just 1.7, so we get 60 minus 30 times 1.7 approximately. And here we get, so this would be 3 times 17, which would be 51, 60 minus 51, this would be 9, and the square root of 9 is just 3 meter per second. So that's the velocity of the person when he is at T2, just exactly at the middle, but before straightening his knees. So now we want to see what happens between T2 and T3. Between T2 and T3, so let me write down V2 is equal to 3 meter per second. So this is important. So between T2 and T3, because the person is just changing its center of mass, we are gonna have an impact at the pinpoint of the swing. So we have a kind of like impact like force at the swing, at the pinpoint, or at the bearing of the swing. So we don't have the kind of like conservation of linear momentum, because there is an impact, linear impact, there is an force, impact like force in the system. So the linear momentum is not conserved. However, if we calculate the moment of all the forces around this pinpoint, then because that force, that impact like force at the pin just passes through the pinpoint, its moment around that pinpoint is equal to 0. And because the angular impulse is equal to 0, then we can use the conservation of angular momentum. So basically here at the middle position here, the forces that are acting on the person and the swing is just one, the gravity, which gravity passes through the pinpoint, doesn't have any moment, and also the impact like force here that exists in the pin, that is created in the pin when the person just changes the position of his knees. That force is also passing through the pinpoint, so its moment would be equal to 0. So therefore we can write down the conservation of energy. So T2 to conservation of angular momentum. So T2 to T3, we can say that sigma MO, the impact of this, 0 to delta T, and that delta T is very, very small. So delta T is just basically going to 0, is equal to HO2 minus HO1. So again, as we argued, this quantity is 0 because those two forces that are acting on the person and the swing are passing through the pinpoint. So O here is just the pin of the swing. Therefore, we have HO2 is equal to HO1. Now, let's write the angular HO3, actually, I should say, when we are going from 2 to 3. So HO3 is equal to HO2. 3 and 2. So what is the angular momentum of the person at 2? So again, as I said, this is middle. This is the middle position. So the angular momentum would be just this length times the velocity, because the velocity now, this person is just rotating around this point. The velocity would be in the horizontal direction, and R would be just in the vertical direction. So the angle between those two vectors would be 90 degrees. So the angular momentum of this person would be just R times velocity, which we calculated the velocity. So HO2 would be R times mv. This would be R at point 2 is just 3 meter times m. Let's say the mass of the person is 80 kilograms, so is 80 kilogram. We will have 3 times 80 times its velocity, and we calculate the velocity, it was 3. So this would be 9 times 80, this would be 720. That's the angular momentum at position 2. Now we have to calculate the angular momentum at position 3, but we have to keep in mind that now R is changed at time 3, because the person straightened his knees. Now R would be 2.7, not 3. So we will have HO3 would be, so let's say this is R1, this is R2, and this is V1, this is M, or let's say 2 and 3, R2 and V2, R3 and V3. So R3 is just 2.7. Now the center of mass for that person is just closer to the pinpoint. So that's 2.7 times 80 times velocity, which is unknown, so V3. because HO3 is equal to HO2, now we can find V3. So V3 would be 720 over 80 times 2.7. So basically this was just 9 over 2.7, and we can calculate this quantity. So this would be 9 divided by 2.7. This is 3.33. So you can see that here the velocity of that person changed. So here we started before straightening his knees, his velocity was 3 meters per second. But as he changed the position of his knees, as he got closer to the pinpoint, his velocity also increased from 3 to 3.33. And you can kind of see that here, because the velocity at this point is just larger than this point, we are going to go higher to this point that is higher than this initial point, because all the potential energy changed to kinetic energy and the velocity was 3 meters. If the velocity changed to 3.3 meter, meter per second, you can see that the person would go higher actually, because now all of that kinetic energy should turn into potential energy. So between T3 to T4, again, conservation of energy. So we can say that U3 plus T3 is equal to U4 plus T4. So at the end position, the velocity is equal to 0, so T4 would be equal to 0. At the initial position, T3, because we are at the reference for the gravity, U3 is equal to 0, so we would basically have T3 is equal to U4, so this would be 1 over 2 m v squared. V3 squared would be equal to, this would be m g. We have to see what is that height over here. So now this is 2.7, and the height would be here. We don't actually know what is the height, so we can just write it down in terms of theta. So the height would be this value, which was 2.7 here, from here to here, 2.7 times 1 minus cosine theta 2. So this would be mg times 2.7 times 1 minus cosine theta 2. Notice that, between when we wrote down the conservation of T3 to T4, we had a kind of like a different reference for the potential energy than we had when we were going from T1 and to T2. So here the reference point was just 3 meters away from the pinpoint when we were just calculating the energy, the change in energy from T1 to T2. But at when we were going from T3 to T4, the potential, the reference line for the potential energy was 2.7 meters away from the pinpoint. But that's okay, because we have to just have consistent reference for gravity between the 2 points that we are considering. So for that, for T1 and T2, we were just using same reference for gravity, and here from 3 to 4 we are using another reference, but it's again the same for 3 and 4, T3 and T4. So that's okay, so that's not a problem. So therefore here we can calculate the value of theta 2, and we kind of see that this theta 2 would be definitely larger than 30 degrees, because here the V3 is just larger, and also 2.7, which is going to show up here, is smaller than the 3 that we had at the beginning. So here we have 1 minus cosine theta 1 minus cosine theta 2 is equal to, so m, they would cancel out. We will have 1 over 2 times 2.7, that would be 5.4 v3 squared, and v3 was just 3.3, so this would be 1 over 5.4 times 3.33 squared. And here we can just find cosine theta 2. So theta 2, we can find it here, and it will be definitely larger than the initial theta that we had, which was 30 degrees. So the person would go higher compared to the kind of like initial position of the motion. So the conservation of energy kind of like simply explains this phenomenon that we all are familiar with. Here from T1, T2, we use conservation of energy. T3 to T4, again we use conservation of energy. But between T2 and T3, because we had an impact in the exerted on the person on the string, we had to use the conservation of angular momentum. And by just using that conservation of angular momentum, we were able to just explain why the person would go higher.